Hi, everybody. Welcome back to the afternoon of day one, and thanks for hanging in there. I know virtual can be hard, so I feel your pain, but Dr. Edward Bork is going to wake you up and hopefully get you as enthusiastic as you were at 8 this morning. So Dr. Bork is the Mattheis Chair in Rangeland Ecology and Management, and he's also the director of the Rangeland Research Institute at the University of Alberta. He's been teaching and conducting research for more than 25 years on the basic and implied topics, including integrated weed control, grazing systems, fire ecology, forage production, agro-forestry, and more recently, the role of rangelands in providing alternative ecosystem goods and services, including carbon storage, greenhouse gas reduction, and biodiversity retention. Dr. Bork has supervised 48 grad students, including 11 PhDs, and he maintains close ties with the ag industry and has given numerous extension talks, including this one. So I will hand it over to you, Dr. Bork.
Thank you, Laura. Good afternoon, everyone. So I'm going to start out by just, recognizing that what I'm going to be talking to you about over the next hour is really a group effort. So title of my talk is Using Grazing as a Tool to Increase Carbon Stocks and Mitigate Greenhouse Gases. But this is really a synthesis of work that's been going on since about 2012. And there's a really large team of people that have helped bring this all together, including postdocs, many other academics, many undergrads, many grad students, both PhD and MSc. So this is a very much a team effort, and it's an ongoing process. Okay, I also want to start out with just, a big picture understanding of the way we've approached the work we've done over the last 9-10 years and flesh out the research objectives. So we started out asking some fundamental questions, such as just trying to quantify the size and stability of carbon stores in the grasslands that we have in Western Canada. And we wanted to understand what is the contribution of different components. So live vegetation, both above ground, below ground, what's in the soil, what's in the shoots, what's in the litter component, what's in the inert mulch that's being decomposed at the soil surface, and so on. We also wanted to understand whether and how grazing increases or decreases this carbon. And specifically, can we predict where and when that might happen and what might be the management triggers to enable an increase or decrease in carbon? And the reason we want that is because if we understand the mechanisms, then we can go to producers with prescriptive beneficial management practices that are likely to enhance that ecosystem service. And the reason we're doing all of this is really to establish a very solid, what I call an empirical foundation that can be used for rewarding ranchers and grass farmers for maintaining and or increasing carbon storage. So I'm going to revisit that goal at the very end, where I throw some numbers at you as to what the potential impact of grazing might be, for example, on soil carbon stocks. Okay, so why soil carbon? Many of you are well aware of this, but I'll just go through this really briefly. So if we look at the different pools of carbon and where they're located, the one that we're obviously interested in trying to reduce is this atmospheric pool of carbon that's in the upper right corner of the diagram. And that's about 800 gigatons of carbon, where 1 gigaton is 1 billion tons. That's with a B. We also know that there's a lot of carbon, for example, dissolved in the oceans. There's a lot of fossil fuel carbon, which of course we're burning through natural gas and oil and coal. But the other pools of carbon that as terrestrial land managers that agronomists are really interested in managing is both the plant biomass. So that's about 550 gigatons, so billion tons of carbon, and the soil carbon. And that soil carbon is around 2,300 gigatons of carbon. So that's about 3 times the size of the atmospheric pool of carbon. And the majority of that, about 1,600 gigatons of that, is soil organic carbon. So that's derived from plant production that then works its way through the different trophic levels. Excuse me. And so an important piece to this is that as land managers, if we look at where could we possibly sequester more carbon, if we could increase this soil carbon pool by even 1%, that would be an increase of 23 gigatons of carbon. And that would be sufficient to offset several years of human emissions. So if you look, there's 9 gigatons that we're adding through human emissions, of which about 3 gigatons is taken up by photosynthesis. So a net improvement in plant growth. So that's why there's so much interest in trying to understand soil carbon and try to increase that. So when we first started our work in 2012, we conducted what was called the carbon benchmarking study. And that went from 2012 sorry, excuse me, to 2015, which we sampled more than 100 grasslands. And you can see them distributed here in the map on the right side. And you can see that they cover a really large range of biogeoclimatic conditions. So brown soils, dark brown, black soils, high rainfall, low rainfall. And we looked at the total soil carbon across all of these different sites and compared it between grazed and non-grazed sites. Using these exclosures, we were quite surprised to find that our non-grazed grasslands were actually about 12% lower in soil organic carbon concentration. So the net effect is that by maintaining grazing within these long-term grasslands, we actually had accrued upwards of 12% more soil carbon. So that was a really intriguing notion to us. Okay, we also inherited another data set, and this is from the former PFRA pastures in Saskatchewan. So these covered 9 community pastures and 33 different paddocks, where we received not only soil carbon data down to 60 centimeter depth, but we also received long-term cattle stocking data from these same paddocks. And why this was important, if you look back at the previous study, we only had presence or absence of animals. So it was either with or without long-term presence of grazing. But in the Saskatchewan data, we actually had detailed information on how many cattle grazed each one of these paddocks, when did they go in, when did they come out, we knew the class of animal, and we could compute these stocking rates. And when we looked at the relationship between long-term cattle stocking and mean carbon mass, we were quite intrigued to find that there was a positive relationship between what we called long-term normalized stocking. So normalized meaning adjusted for rainfall, because we know high rainfall areas should produce more biomass, and that should fix more carbon, and that should enhance soil organic carbon. So we found a positive influence of grazing on soil organic carbon in the top 6 inches. Excuse me, sorry, I have a frog in my throat. And that's even when normalized for rainfall. And so that suggests that the signal, if you like, the ecological signal of grazing on these grasslands was actually greater than that of precipitation alone. Again, reinforcing this idea that grazing is certainly compatible with not only maintaining, but even increasing carbon. So when we asked the question, how much carbon do these grasslands contain? The numbers were quite impressive. So if we look at the land use differences on the right side here, we see that our native grasslands stored a much higher level of carbon overall compared to both our annual crop systems and our introduced forage systems. That'll let some more air into this room. Okay, so if we look at that net increase in carbon, we see that there's about a 30 to 40% higher total carbon mass. And these are conservative estimates because we only actually measure the carbon within these benchmarking sites down to about 30 centimeter soil depth. Within the mixed grass prairie, we had roughly 50 to 60 tons of carbon. And within the foothill montane environments, we had upwards of 180 tons of carbon. So we had very, very high levels of carbon that were accumulating long-term within these systems. Most of this carbon was in the soil, although the surface mulch layer, which is really that dead, decomposing layer of organic material that's in various stages of decay on the surface of the mineral soil, That was also a very considerable pool of carbon, up to 15 tons of carbon per hectare. Okay, we also looked at some different components of nutrient cycling. So for example, one of the things that we found across our benchmarking sites is that grazing consistently altered plant composition, and in particular, increased the plant diversity. And the diversity components that increased were largely these broadleaf dicots. So species like dandelion or naturally occurring legumes, the Asteraceae, so any of the broadleaf plants. And why is that important? I'll show you momentarily. We also found that when we compared rates of litter breakdown or decomposition between grazed and non-grazed areas, we found that litter actually decomposed faster within grazed grasslands. And you can see it here between these curves. These are basically decomposition curves for both the foothills fescue in southwestern Alberta and then the aspen parkland in central Alberta. And so what does that mean? Well, it means that the microenvironment created on the soil surface by virtue of the grazing animals themselves, whether it's because of alteration of the amount of nitrogen available or the relative humidity at the soil surface, or by compressing the litter into the ground, it basically accelerated the decay and turnover of litter, which again is not surprising, but that could be an important agent or mechanism to carbon sequestration. We also found that species like Kentucky bluegrass, which is a grazing tolerant invader, very common across the Dakotas, Saskatchewan, Alberta, when it comes to the role of grazing on many of these grasslands, you see these grazing tolerant species do really well. And this happens to be an introduced agronomic that has escaped and is widely proliferating. We also found that Kentucky bluegrass, for whatever reason, actually decomposes particularly rapidly, much more rapidly than many of our native grasses, in part because it has higher levels of what we call extracellular enzyme activity, which are basically the enzymes that microbes produce that are responsible for turning over carbon and nitrogen within that litter. So bottom line is what I'm getting at is there appears to be a grazing-induced change in plant species composition that in turn is triggering changes in the rate of litter turnover and potentially carbon accumulation within the soil. Okay. We also went back to our benchmarking study and looked at this collective, because we had so many sites here, we had over 100 sites to look at some of these complex relationships. And most of the studies done that look at these kinds of data are often looking at 1 or 2 or 5 sites, not over 100. So we conducted what was called a path analysis. And we worked with Dr. Eric Lamb at the U of S to do this. Basically, what it boils down to is we wanted to understand the presence, absence of grazing and how it tweaks soil organic carbon way over here on the right. And these are the different paths. I'm not going to get into detail on the paths, but there are 2 mechanisms or drivers, if you like, through which grazing actually changed soil organic carbon. The first one is grazing actually increased forb mass. So these are the broadleaf plants, the ones that I was just mentioning. So species like the Asteraceae and the legumes and so on. Those in turn actually increase litter carbon, which in turn directly increases soil organic carbon. So you can see the direct linkage between how grazing is actually driving soil organic carbon change. The other one is on the graminoids. So the graminoids meaning the grasses and the sedges. And in that case, the grazing actually reduced the carbon to nitrogen ratio of the graminoid biomass. Now, a lower carbon to nitrogen ratio is actually a good thing because it means that that carbon can be more readily incorporated or cycled, if you like. So microbes can incorporate it back into the organic pool much more readily. Ironically, the pathway was identical. So once grazing occurred, it reduced that carbon to nitrogen ratio. That increased litter carbon, and that in turn increases soil organic carbon. So both of those pathways, an increase in forb diversity and forb biomass, and an increase in grass quality, both contributed to soil organic carbon increases under grazing. We did one last study that I want to touch on before I get into the AMP work that we did, which is to look at how does carbon actually move, especially from above ground where it's photosynthesized by plants and down into the soil. So many of you, I'm sure, have heard Christine Jones talk about the liquid carbon pathway, and I first heard her a number of years ago talk about this carbon movement. But when I went to try to figure out how many people have actually measured where the carbon is going and how, let's say, defoliation alters that carbon movement, I couldn't find anything. And so we actually did a study out at the Mattheis Research Ranch, which is close to Brooks in southeastern Alberta. And we used carbon-13, which is basically an isotope, to track over a several week period, where does that carbon that's fixed go? And so after we dosed these plots basically with carbon-13, we found that more than 1/3, so 34.5% of that carbon-13 had moved out of the chute and was down underground within the soil at 21%. So almost a fifth of it was within the mineral soil within 24 hours. That's how quickly it moves down into the soil. So that gives you an idea how that carbon is actually being fixed, taken below ground, and some of it is being given off through root exudates into the soil matrix, where of course it's made available for microbes. The other thing we found, because we had different defoliation treatments, is that we found that more intense defoliation. So if you take off more of the leaf area, force those plants to allocate more of that carbon to the roots during the first 3.5 weeks, 25 days. So by altering the pattern, just the intensity pattern of defoliation, you're changing how the carbon flows. And the implication of this is that could you have these very short, intense bursts of defoliation that stimulate carbon allocation to roots and to the soil matrix, and therefore create this positive feedback cycle? It's an intriguing idea, but I think we need to have potentially more work on this. So we do plan to do more on this. Okay, so I'm going to springboard now for the last half hour or so into our AMP study. So this adaptive multi-paddock grazing trial took place from 2016 to 2021. It was led by Mark Boyce. I was involved. There are many others involved, and they're listed on the front slide of my presentation. So we basically looked at AMP grazing at up to 32 ranch pairs, and they were kind of sprinkled across Alberta, Saskatchewan, and Manitoba. We evaluated all kinds of different components of soil and grassland function. For example, we recorded cattle management activity, forage production and use, water infiltration, carbon stocks in the soil, greenhouse gas fluxes, and microbial activity. And so before I get into this too much, most of you probably know what AMP grazing, but I just want to make sure that we define it clearly. So AMP stands for Adaptive Multi-Paddock Rotational System. So in Canada, the work that's been done and published basically shows, at least Western Canada, 50 to 70% of producers rotationally graze. So some kind of rotation. But in all likelihood, less than 10% use these adaptive multi-paddocks. So highly controlled means whereby you're using a lot of subdivision of pastures into smaller areas, high densities of grazing. There's lots of different names out there like planned grazing, mob grazing, management intensive, high intensity, low frequency, holistic, regenerative. That often these are all bundled together. The principle, simple. You take a large area, subdivide it into much smaller paddocks, use really high animal densities for short periods to get more uniform forage use. And therefore, if you get more uniform forage use, you should also facilitate a longer recovery period prior to regrazing. So your plant should be in better vigor, grow back faster, produce more regrowth, and so on. So you're taking, these large paddocks with unregulated grazing and breaking it up into smaller areas, and then confining those animals. Here's the distribution of our ranches, our ranch pairs, and you can see there's some in southern Manitoba, there's some in southern Saskatchewan, and some sprinkled across Alberta. And then we did do fairly comprehensive management surveys with each one of these producers, where we collected information on land area, herd size, stocking rates, how many pastures, how big were the pastures, and then tried to get detailed information on patterns of grazing and rest. And so, for all of these pairs, this is basically what we're looking at. We had a AMP producer, which is I've depicted here, And in some cases, the neighboring, so NAMP is really the neighboring, might have been a true continuous grazer where they put their animals in May 15th and they stayed in there till the end of October. So the best way to think about this study is that the neighbors are really a conventional grazing practices by industry because they're a random grab bag, if you like, of what the industry might be. So in some cases, the neighbors were continuous, but there were other cases where the neighbors might have been a slow rotation or even a nearly or an outright AMP rotation. So there's a lot of variation among the ranches examined. The only thing that was a given is that there was always at least one AMP within each pair. But within a pair, you could have very strong differences or you could have much smaller differences. Okay, so let's go through what we found. So question one, what are the management differences that exist between AMP and non-AMP beef cattle operations? So this has been published. And we'll just start out with some of the basic background information. So between the AMP and the neighboring to AMP, they had similar cultivation histories. About 3/4 of the ranches, basically, we were working with land that had previously been in crop at some point and had been since seeded down. The average time since planting was close to 20 years for both data sets, for both AMP and the neighbors. One difference that I think is interesting, and many of you will find interesting, is that the AMP ranchers were more likely to seed native species and also to use more diverse forage mixes. So this is the proportion of ranch operations with seeded pasture land. And if you look, the AMP were more likely to use native, whereas none of the neighboring to AMP had utilized natives at all. So close to 20% of our AMP producers actually utilized native, at least one native species within the seed mix. And if you look at the more complex seed mixes, especially the mixes involving at least 5 species, you can see that AMP producers on average were much more likely, just about 3 times more likely to include more complex mixes. And this is likely a philosophical difference in the management style. They recognize the importance of having a high diversity of forage species within their pasture production system. Okay, land area and pasture configuration. So AMP ranches basically were much larger, and so upwards of 3 to 4 times larger on average, and not surprisingly, they also had larger herd sizes. Now, this is interesting because on one hand, it could suggest that AMP, in order to be likely to implement AMP ranches, you have to attain a certain size. That may or may not be true, or it could simply be that larger ranches were more likely to be more progressive in terms of the things that they were going to try, and therefore likely to try AMP grazing. So there's a couple ways that you could potentially interpret this. One thing that is very certain, though, is when we looked at the biophysical layout of the pastures, there were huge differences. The AMP ranches basically were running an average of 60 pastures, whereas our neighbors were running generally less than 10 and usually closer to 5. Whereas the pasture sizes were the opposite. The AMP were usually working with an average pasture size of about 20 hectares, whereas the neighbors were working with a pasture size upwards of 120. So the physical layout, very, very different between these two. Another really important component here is when we looked at how these different ranches actually grazed, there were profound differences in how they grazed, but not necessarily how much they graze. And the way I want to stress this is as this. So if we look at the stock density, and stock density is a very important metric. So if you talk to people that practice holistic grazing, you often talk about something called herd effect, which is really tied to the stock density, the number of animals per unit area. But it is an instantaneous measurement. It's taken at one point in time. And it's true that the AM producers basically had more than a 20-fold higher average stock density at any one point in time. But stock density is not the same as stocking rate. Stocking rate is basically a metric that's used to quantify the total aggregate forage demand over the entire grazing season. So it factors in not only density, but how long are these animals grazing? And when you factor that all in and you compute out the actual stocking rate, which is animal unit months per hectare, there's actually statistically no difference. Now, it looks like the AMP is maybe a little bit higher, but statistically, we could not attribute there being a difference. So what this really means is that while it looked like the AMP producers might have been grazing a little bit heavier, they really aren't grazing that much heavier. What differs is how they're grazing by using these high stock densities. It also is reflected in the length of the grazing season, because when we ask producers, when do they start grazing, when do they end grazing, which is some of the information we use to compute the stocking rates, we found that the total grazing season length was considerably longer, like 40 to 50% longer for the AMP grazers. So that means they are being more progressive in starting grazing earlier and ending grazing even later, stretching out, if you like, the length of their grazing season. And you can see that by the start date here and by this overall grazing period. So what differs is how they graze, not how much they graze. Last, when in terms of the computation, if you like, of the management factors, we computed something called a rest to grazing ratio. So the rest to grazing ratio is really the number of days of rest for each day of grazing during the early part of the growing season. Why did we do this? Well, because what we do know is that many of these systems are really intended to have very short animal impact periods and then a lengthy rest period to facilitate recovery. And many of our AMP producers were very clear that they had, let's say, a minimum length of recovery of 30 or 60 or 40 days or 45 days before they would bring the animals back in for a second pass, if at all. And so that's why we computed this rest to grazing days ratio. And we basically found that there was a really nice segregation between the AMP producers that often had at least 6, an RGR of at least 6, and often more than 40, whereas the neighbors were typically below 6 and most often 0 to 2. So again, there's that impact. How animal impact is applied to these pastures is sharply divergent between our two treatment groups. The last thing I want to stress is one thing that really stood out here is that both groups are still highly variable in their management tactics, even within the AMP and certainly within the neighboring to AMP. This is what we call an ordination, which is basically a scatter plot of how these different producers and ranchers differ in terms of the management practices they apply. The implication of this is that simple categorical groupings of grazing are really not representative of what's going on in the real world. And I mention this because many studies that try to do this and report in the literature, for example, will lump together all rotational grazing and look at rotation and continuous and treat them as nominal classes of treatments. And I'm going to make the opposite argument that the use of these really specific grazing metrics are actually better and more powerful in explaining the impact of grazing on things like forage production, carbon, and so on. So the devil is in the details, so to speak. We need to understand the detailed management actions. Okay, question 2, how does AMP grazing alter grassland production and forage use? And many of you will be very interested in this. So this was addressed by Jessica Grenke, who is a PhD candidate. And I only have one data slide from Jessica's work, but I think it's some very interesting results. So this graph on the left shows above ground biomass. And so based on our sampling of peak above ground biomass in the AMP grazed grasslands and the neighboring areas, we actually found that the AMP areas produced about 20 to 25% more biomass. So it means they're more productive. And that occurred despite higher utilization. So it means that even though we're removing more biomass, the fact that we're using these high stock densities with short bursts of grazing and then an extended period of recovery, it's still enabling for greater grassland biomass to be produced, which, interestingly enough, suggests that we may have what's called compensatory forage growth going on, which basically means that the plants are producing more, with grazing than they would as compared to if they were not being grazing, at least under this particular defoliation regime. So that's the important thing, because remember, we got grazing going on in both of them. So it's one of those situations where it appears we can have our cake and eat it too. We can have our forage and eat it too, but provided we're grazing it a certain way. Okay, third question we asked is, does AMP grazing alter water infiltration? So there's many folks that have argued, including out of the Holistic Management Center, that AMP grazing or these types of pulse grazing systems will improve water infiltration. So we actually tested it, and we recently published a paper. Tim Daubert was a postdoc on the project. And so here's some of his results. So indeed, we found that the soils exposed to AMP grazing for this lengthy period of time, and remember, these are at least 10-year-old treatments and usually longer, that AMP grazed soils had more water capture for plant growth. So you can see there's about a 40, 50%, maybe even 60% increase in water infiltration rates. So peak water infiltration under AMP grazing was almost 100 millimeters. Under the conventional or the neighboring grazing, it was closer to 50. So what that means is these longer rest periods following these pulses of defoliation appear to create soils that whatever reason, whether it's porosity or organic matter or a little bit of all these different things, it's improving water infiltration. Now, we also found, just to revisit this idea of stocking rates, okay? So when we looked at infiltration rate against the RGR, we found, as we would expect, a positive relationship. So if you have that longer recovery period following that pulse of grazing, yes, your water infiltration rate goes up, but overall stocking rate still had a generally negative effect. So you can still have excess stocking, which presumably by compacting the soil and reducing water infiltration, you can negatively impact the hydrologic cycle. So again, it's how you graze, not necessarily the absolute amount of grazing. So you can still overgraze and you can still reduce your water infiltration. Okay, does AMP grazing alter soil microbes? So we were interested in soil microbes because that's a big part of the soil ecosystem. And so there's a PhD candidate, Upama, that's basically been working on this. And so I'm going to share with you some of the results. I'm not going to go into a lot of detail other than to say, absolutely, AMP grazing had a very profound effect in changing many different indicators within the soil. And here's some of them. So if you look at the graph on the left side here, the adaptive grazed soils had a lower microbial biomass carbon to microbial biomass nitrogen ratio. So again, that would be reflective of potentially the rates of biochemical cycling, so carbon turnover within the soil. You can also see that higher stock densities, so that's density, not stocking rate, reduced the fungi to bacterial ratio. And so again, the ratio of fungi to bacteria is important because fungi are notorious for being really important for carbon stabilization within the soil. And soil microbes were also directly affected by cattle stocking rates. So again, we see this shift towards a lower MBC to MBN. And then one other slide I'll just touch on, and this one does a really nice job just showing the differential impact of AMP grazing in changing the overall microbial community. So this is bacterial diversity within the soil. This is fungal diversity within the soil. These are just two different diversity metrics, but they basically show the same thing. The blue boxes are the AMP means. So if we compare mean bacterial diversity as compared in the AMP versus the neighboring ranches, we see generally higher diversity of bacteria under AMP grazing. We see the exact opposite response for fungal diversity. So you can see the AMP ranches are lower in fungal diversity. So again, AMP grazing is definitely changing the microbes within the soil. Now the question is, what are the direct linkages to some of the other ecosystem functions? And that is still to be determined. Okay, next question we asked is, how does AMP grazing alter greenhouse gas emissions? We published a couple papers from this. One is a lab incubation and the other one is a field assessment of the greenhouse gas emissions. So Barat, Resta, and Zalong Ma were the ones that basically led this. I'm going to start out with the lab incubation. Now, you might be wondering, why did we do a lab incubation? Well, this is why. So we took soil from these different grasslands, brought it back to the lab, and then we subjected it to either different temperature treatments or different moisture treatments. I'm not going to present the moisture treatments, but I am going to show you the different temperature sensitivities. Now, the important thing here is that if you look at all these values on the x-axis, they're all negative. So these are methane consumption levels. So methane is a greenhouse gas. It is much more potent than carbon dioxide. And of course, methane often gets implicated when you talk about methane emissions from cattle because of enteric methane production from the rumen, the microbes that are breaking down coarse forage in the rumen. Now, when you have negative methane values, that means that there's a net removal of methane from the atmosphere. So these are basically methanotrophs. And so the way that that word basically gets translated, they're methane eating, basically. They're consuming methane. So it is a good thing to have a negative value within the soil because it means there's more methane being removed from the atmosphere. And so that represents a good thing because that means we're removing a potentially potent greenhouse gas from the atmosphere. And the lower it is, the better it is. Now, let's look at the two treatments. So the blue bars are the AMP and the orange are the neighboring to AMP. And what's interesting here, you can see the pattern, but the AMP conditioned soil, and I say conditioned because the way I like to think of it, it's the grazing treatments in the field that created the microbial communities. And when we bring this into the lab and then we look at the methane consumption, it tells us whether the conditioned microbial community is able to increase the uptake of methane. So in this case, AMP conditioned soil, so that microbial community had greater methane uptake, which is a good thing. And it's particularly apparent at higher soil temperatures. So when you get warm conditions like we had in 2021, or such as we might have going forward if we have prolonged climate change, this could be a very good thing because it means these AMP conditioned soils could be more effective at removing methane. So we hypothesize it's due to the changes in the microbial community that I outlined earlier, and that will be one of our next steps is to go back and try to parse out what's going on in terms of the specific microbial responses. Okay, we also looked at field greenhouse gas emissions. Now, one of the challenges with trying to measure greenhouse gas emissions in grasslands per se is that they're highly variable in space. And so unfortunately, we weren't able to find a difference in CO2 fluxes. So that's the primary greenhouse gas relative to the grazing treatments per se, but we did find, again, this increase in CO2 flux, and you can see it here with total cattle stocking rate. So this is our stocking rate, and that was particularly true in our moisture grasslands or high rainfall productive grasslands. And so the implication here is, again, we want to avoid excess stocking to minimize carbon loss, okay? Another interesting thing that we found, because not all of our ranches had a history of being cultivated at some point in the past. So remember, these areas had been seeded down many years ago, in most cases 20 plus years ago. But the native, so the never cultivated grasslands were actually a much stronger carbon sink. This is really interesting because it suggests that where we've cultivated our soil, and even if we've only cultivated it for a decade or two, and then we go plant back perennial forages, thinking that they will go right back to their original kind of functionality, that's not necessarily the case. As we found that those native grassland soils were actually a much stronger methane sink relative to the areas that had a history of cultivation. So there's a legacy effect of prior cultivation, even if it's decades ago, that we really need to be aware of. Okay, this last question, which is a really important one. Does AMP grazing alter soil carbon stocks? So this is Lau Sobrino's work. He's currently at Olds College, and this is a work in progress. And so I'm going to share with you 3 different slides. So some of this is really good news. Some of this is maybe not so good news, but to be determined. So early on, when we looked at the depth of the AH horizon, so the AH horizon is really your topsoil. It's your enriched topsoil layer that might be 10 inches or 12 inches, or if you're really lucky, 14 inches if you're in a high rainfall area. And what we found is that there's an interaction of grazing treatment with stocking rate, where we could get away with a higher stocking rate if we were using AMP grazing. So that's this pink line here, suggesting that, look, AMP grazing might allow us to utilize these higher stocking rates to elevate soil carbon. And we were seeing the increase both in the topsoil thickness, so the amount of that enriched topsoil, but also in the soil organic carbon mass. So this would be the soil organic carbon mass increase. And we can also depict this if we look specifically at this rest to grazing ratio. So these are the modeled responses in both AH layer depth, so the thickness of that topsoil in centimeters, and this is soil organic carbon mass in tons per hectare in relation to different RGRs. Now, if we have no rotation at all, so that would be, for example, this blue line, so rest to grazing ratio of 0. So that means there's no rotation, you're not using elevated stock density and no recovery period at all. The animals just have free choice all year round. You actually see that there's a negative relationship between stocking rate and soil organic carbon. However, when you start implementing these different lengths of rest periods, so 20 days, 40 days, 60 days, 80 days, and even higher, you can see that there appears to be this potential increase in soil organic carbon mass. So that would be good news. However, just in the last 2 days, we did another further adjustment where we took our data and we computed something called equivalent soil mass. So equivalent soil mass adjusts for the fact that different grazing treatments can alter soil bulk density, and bulk density is really a major determinant of how much carbon is going to be there. So when we did that equivalent soil mass calculation, we still see that the AMP grazed soils follow this pattern of having more soil organic matter accumulating near the topsoil. In this case, it's specifically within the 10 to 30 centimeter soil depth. However, this could be offset by a potential reduction deeper down at the 60 to 80 centimeter soil depth level. So this is something we're going to have to follow up on in much more detail. So this is very preliminary. This is not published yet, but what is interesting is that AMP grazing may be shifting where the carbon is stored. And then there will be secondary questions as to how stable is that carbon, and or what are the implications for long-term carbon storage and greenhouse gas offset. We also, when we looked at the relationship between soil organic carbon and looked at the relationship between exotics again, and I mentioned earlier this linkage to Kentucky bluegrass, which we found both in Alberta and we found it in Saskatchewan. And now within our AMP study, we're also finding it, that where we have these exotic species, and by exotics, I'm not necessarily talking about noxious weeds. I'm talking about, you know, species like timothy and quackgrass and smooth brome and bluegrass and all those kinds of species. And if we have a lot of those species, we actually tend to see this positive influence on soil organic carbon. And that happens regardless of whether it's under AMP grazing or not. So there may be other factors that are really important here as well in driving soil carbon stock change. Okay, so I have 2 ways I want to present the summary. This is the summary that takes us basically to the end of the presentation, but I have one more data slide. So some points that I hope you take away from this. First of all, grasslands are really important and very large storehouse for biological carbon that, in my opinion, is very significantly undervalued by society. There are very complex effects of grazing on grasslands, whether it's diversity changes, composition changes, microenvironment, nutrient cycling, and all of these can actually help contribute to carbon accumulation. And I fleshed some of those out. Grazing, including AMP grazing, may be a useful tool, especially if done at the right stocking rates, to enhance plant production, water capture, so those infiltration rates, and maybe soil carbon. And really, we probably need we need policy changes at this point that really recognize and fully value this grassland carbon and incentivize ranchers to maintain and exist and increase it where and when possible. So I want to leave you with this closing thought. So I've been working on a roll-up paper from our benchmarking study where we asked a very simple question. What's the potential value of the added carbon due to grazing in Alberta? So remember, the benchmarking study is where we had grazed and non-grazed areas for long, long periods of time, and we quantified the carbon stocks in there. So this is the results of this roll-up work. So across Alberta, we estimate there's about 3.8 million hectares of grassland that is currently grazed, and it contains about 362 million tons of carbon. And these are conservative estimates because we're not going down and accounting for the deep carbon. In that benchmarking study, we only went down to 30 centimeters. So these are conservative values. We also estimate that grazing on about 95% of these lands has increased carbon stock because we have, remember, the comparative data between grazed and non-grazed. So grazing has increased that carbon stock by over 17 million tons. Now you might go, well, it doesn't seem like a whole lot, but it is, because we know what that carbon is worth. We know that according to the federal carbon tax right now, as of January 1st, 2022, that carbon is worth $50 a ton per CO2 equivalent. So if you apply that multiplier onto that carbon stock, including the fact that, right, you have to take that 17.1 multiply by about 3.6 to convert it into tons of CO2, then you multiply by 50. The dollar value associated with that is over $3 billion with a B. That's a lot of carbon, and it's a lot of dollar value that's potentially being missed. So that's why I make that point that it's time for this carbon to be recognized and fully valued, and for those maintaining and enhancing it to get paid for it. The graph on the right here just shows where the biggest potential benefit in carbon stock exists. And two things on this. One is you can see that obviously the greatest potential value of carbon is in the Aspen Parkland, followed by the foothills fescue of Alberta. However, that's not to say that, for example, the upper foothills or Montaigne do not have a lot to contribute. It just means that there's less grazable land or land that's being grazed within that area. The only area out of all of these different regions that really doesn't respond overly positive to grazing are the really dry, arid systems. So largely the mixed grass, especially the dry mixed grass. That's the only zone where we really don't see a big benefit in soil carbon due to grazing. Okay, I know that was a lot of information. I crammed it into like 40, whatever it was, 50 minutes. So I've got about 10 minutes left for questions. So I'm happy to entertain any comments or questions.
Thank you so much, Dr. Bork. And you're right, that was just a ton of information. I think I would have to listen to it 3 more times to even get a third of it. And it was fascinating to hear that there are soil microorganisms that can eat methane. That was news to me. Okay, so we do have a question from Scott Gillespie. Scott, do you actually want to unmute yourself and ask it yourself so you can have a bit of a conversation?
Sure. Are you able to hear me now?
Yep.
Loud and clear.
And you can see me? Did my camera come on? I don't see you, but
I still have my slides on in case I got to go back to them. So
okay. Well, anyways, so my question was, it looked like the main effect for building carbon was because you've got that constant cycle of the stressing, and then they work hard to regrow, and then you stress them again. Like it's that constant cycle of grazing them before they get too mature, and then they go back to vegetative, and they keep going through that cycle. So I was wondering if we have like annual forages or even cover crops that get grazed, say near the end of the season, and then they either die off or like either winter killed, or very soon in the spring they're terminated so that we can plant the cash crop. Are we gonna, my guess is that we're probably not gonna get much carbon in there because they're not gonna go through that regrowth phase. What do you think on that?
Yeah, so yes, I agree with you. So there's a couple really important things. So one thing about these perennial systems, and there's really two parts to your question. So one is the legacy effect of the annual cropping, and the way I would answer that is like this. If you look at our perennial grasslands, and especially our native grasslands, okay, what's notorious about them is that the vast majority of their biomass is below ground. And for example, the work that was done a long time ago by Robert Copeland in Saskatchewan clearly showed that about 85, 90% or more of the biomass in those mixed prairie grasslands is below ground. And even at Kinsella, at the U of A ranch, where it's a fairly favorable moisture regime, we still have a root to shoot ratio of, let's say, 4:1. So that means 80% of the biomass is below ground, 20% is above ground. So what we're really managing is the tip of the iceberg. And it's that accumulation of all those roots over many, many, many years, decades, centuries that really has built that soil carbon. Now, if we cultivate it, and really what ends up happening, Walter Williams used to call it the furnace effect. You warm the soil, you aerate the soil, that enables the microbes to go bananas, and they basically attack and break down that soil carbon very quickly, and they release a lot of it. And so globally, 30 to 50, even 55% of that carbon gets blown out very quickly. And so cultivated soils, yes, they go to a new equilibrium, which is much, much lower than what they were historically under those perennial systems. Now, I'm going to answer your question two ways. Okay, so if you now bring in, let's say, tame forages, so they're perennial, but you bring in tame forages, and I'm going to pick on, let's say, smooth brome and crested wheat, okay? If you plant those, they may not have the same root to shoot ratio or the same root profile that those native grasses did. Why? Well, because they're agronomics in part, and we're breeding them to produce stuff above ground. We want them to produce something above ground because we want to graze it. And so it could be that they're not as deep rooted. There's still lots of root mass, but it's maybe much shallower. And that's why very possibly, for example, where we're seeing a lot of these introduced species coming in, these agronomics invading into our grasslands, there's a couple possibilities as to why the carbon's going up. One is they're just very prolific in terms of their shallow roots, which a lot of them are. And second of all, maybe because we're just adding outright the carbon. Now, would we expect those introduced forage stands to produce the same amount of carbon? Not necessarily. Not if they aren't putting the same amount of biomass below ground as those native systems did. Would they put in more than an annual crop system? Yes, very likely, because if you look at how much biomass is below ground, let's say in a smooth brome stand or a meadow brome alfalfa stand as compared to a wheat field, you're going to have far more biomass below ground under the perennial system. So now to come back to your question, if you're simply putting in cover crops and your annuals, those annuals are really striving to complete their life cycle within a given year. And so again, they're going to produce, their root to shoot ratios are not going to be the same as the native grasslands. They're not even going to be the same as those perennial forages necessarily. So, unless it's a perennial system that is built up this really large root system, I wouldn't expect them to put in as much carbon. Now, will that cover crop put in carbon, more carbon maybe than a wheat field or a canola field? Yeah, quite possibly. So the differences are in the rank order, right? So I'm hoping, Scott, that I'm answering your question about how you would kind of build up that soil carbon. Let me put it this way. As Henry Jansen used to, say, I read this, and I know he said it many times, if you don't fix the carbon, you can't put it into the system. So it's all about more productivity, period. So how these AMP systems are really building that carbon, to me, it might be about optimizing recovery and therefore that compensatory growth. I think that's really intriguing, because if you can get more plant production, that's more fixation of carbon, and that has to lead to more carbon, right? And then it may also come down to this increase in diversity and this change in the quality of the vegetation, which in turn could affect the fate of that carbon. So if we can get it into the soil in a more recalcitrant, so resistant form, then it would contribute to a further increase in the soil carbon pool.
Yeah, that pretty well answers the question. And it was more I was kind of, it was kind of, I'm still kind of processing things that I've been trying to wrestle with, is how that all works. And I think that answers a lot of the question on how these perennial systems build up the carbon. It's because it's that long-term cycle of them always. It's the recovery part that they need, and maybe that's why the AMP and all those ones, you know, they have such a much longer recovery. So
yeah,
that is interesting. I see another question, so I don't want to take up all the time.
And if you go back to what plants need to grow, if you deal with a year like 2021, and you got moisture limitations, if you get more water in the soil and more water capture, now you've overcome another limitation, right? So that could also explain potentially higher plant productivity. So, but it all goes back to, if you don't fix it, you're not going to store it.
Yeah, and where I am in the brown soils, it was kind of interesting that one last slide just showed that, you know, in the real low moisture, typical low moisture areas, yeah, it's going to be a much longer process, and much lower expectations for what you can get out of the system. So.
Okay, I see Ian has his hand up, but before we go to Ian, Matthew Weens, did you want to unmute yourself and ask your question from the chat box?
Sure. Can you hear me here?
Yep.
Yes.
I just wanted to endorse your statement there that the land managers maintaining or enhancing grassland carbon should get paid for it. Have you thought of how they could get paid for it? I know lots of people are working on various schemes, but I'm not sure that I've seen anything that really captures my imagination yet.
Oh, I knew someone was going to ask that. Yeah, I think about it all the time. I like to consider myself an information broker. So I like to consider that what we're doing is creating the underlying empirical database that eventually will get so overwhelmingly clear that the policy folks cannot turn away from it. And I to answer your question, I used to think that it would be driven through more of the regulatory, market top down. I don't think so anymore. I think that there's there's what I call the additionality roadblock. So if it isn't new carbon, I think there's a lot of politicians and senior policy folks that just throw their arms up and go, no, we're not going to pay for something we're already getting for free. And I think that's a big mistake, because while we're trying to pay people to incentivize to build new carbon, we're actually losing other carbon, because land use change is still going on of marginal land. And that's where I really see that we should be first trying to incentivize those producers not to convert marginal land for short-term gain, which then eventually we're going to try to want to put back into perennials. So I think it's going to be driven more so by the involuntary, the voluntary market, which is consumer driven, and by large corporations. I've have a number of discussions going on with different groups that are working with industry. And it's because those industry partners want to make sure that the products they're producing, whether it's agricultural products or whether it's just trying to find offsets for what they're doing that are socially responsible. And I think that's where it's going to be driven. I don't think it's going to be driven by the regulatory, so by the feds. I really don't see it at this point. I think it's going to be driven by the voluntary market, and that's going to come from the corporate sector, and it's going to come from the private consumer sector. That's where I think it's going to come from.
Just to follow up what you said about as we're looking at carbon already there, we're forgetting about we're trying to incentivize new carbon. Meanwhile, we're converting marginal lands. I really see that as an unintended consequence of the clean fuel standard and renewable diesel and and the drive to push up canola production, I expect if we're not careful, we'll have that unintended consequence of converting a whole lot more grassland across the prairies.
I 100% agree with you, because short-term economics and fiscal survival really drives a lot of producer behavior. And right now, with $22, $23, $24 canola, that's going to drive a lot of crazy land use change.
Thank you.
Yeah, that was a good point, Matt. Okay, Ian, you're up.
Hello. Is the microphone working? Thank you.
Yep.
Oh, yeah, thanks for the presentations. And on this point about carbon and getting paid for it, absolutely. An easy way to measure is by the soil organic matter. And there should be there has to be some kind of incentive. The market system, and as suggested, the carbon credit payments system, that a lot of these corporations are looking to reduce expenditures a lot of the time, and that's what everybody's looking to try to do, is reduce expenditures. But Mother Nature doesn't account for what we do, and what we're doing is continuing to use fossil fuels and add fossil fuels to our problem. And we can certainly make some difference with the carbon cycle, but all of nature put together is what it is. And it's only going to use the amount of carbon that it can use. It cannot use excessive carbon. And so there has to be a better plan. And it will take some actual planning. And this is where people need to be pushing, is what I'm feeling. And the forage and grassland people are promoting much better use of cattle in the grassland management. And that's exactly what's needed. And how we get better pay for that, that's a couple of ways. But the people that buy the products, I don't know how much they know about looking after land. Everybody says they don't know much, but we have to all realize this. Everybody that's living on Earth has to realize this. It's urgent.
Yeah,
as far as the climate goes.
And Ian, I'll just add one thought to that I think too often we get hung up on maximization rather than optimization. And it's a totally different management philosophy to think optimization. Because that may mean accepting a 20% lower output or yield in exchange for a 5% bump in profitability. And some people are unwilling to accept that. And of course, in agronomy circles, that's probably a bad word. And I live out on a mixed farm. So we have grain and we have oil seeds and we have cattle northeast of Edmonton. But I can see what's going on, and there's a lot of that maximization mentality that's gotten some folks into a lot of trouble. And that's the cycle of how these, unfortunately, the state of agriculture today, that we're very much hooked on maximization rather than optimization.
Okay, we're pretty much out of time, and I just want to thank Dr. Bork for an incredible presentation and for making our brains work at this late stage in the day. And thank you also for generating that level of conversation. We've had more conversation here than we have in some of the other sessions, so that's awesome. So clearly people are thinking about trying to figure out how to get cattle on the landscape again. It seems like they could be a solution here. So thank you for that.